Hi, you're watching AC's 8-Bit Zone. Today I'm going to show you how to make an IC tester for really low cost. This is a Programmable Logic Array tester, or PLA. This chip is used in the Commodore 64, but I suppose this tester methodology could be extended to test a lot of different kinds of ICs. Anyway, this is going to be really low cost. I'm going to show you how I put together the hardware, then I'll show you how to get the Arduino code, and it can make for a long video, but I'll put some jump-in points down below so you can jump to a specific part of the video. If all you care about is building the hardware, getting the code, and playing with it, you could probably get through the video in about 10 minutes. But I did want to put in that whole middle section in the video where I go over more of the inner workings of the PLA, and I show you a lot of the details and where to get more information. So if you like that, I just thought it'd be better to include that. And anyway, there's a lot to cover, so we better get started. Okay, so here's a little bit of a close-up, and we'll take this to the bench, break it down, and get a much more detailed look at how to build this. But for just a few simple components, this is a Arduino board. It's the Mega 25, I think it's the Mega 2560, but I'll show you that in just a minute. It's a Arduino shield. It's a ZIF socket. Yeah, and you can use the 28 pin or 40 pin like I've used here, and a volt capacitor, some wiring, some LEDs, some resistors for those LEDs, and that's it. So let's get this over to the bench, take it apart, and I'll show you how to build this yourself. Alright, here is the entire bill of materials that you're going to need to build this. This is the Arduino Mega 2560. This is the expansion shield. This is a bulk capacitor, something in the range of 2 microfarad to 22 microfarad would be enough. There are 8 LEDs and 8 resistors to go with that. Mine happen to be green. They're about 2.2 to 2.6 volt forward drop LEDs, but that's going to vary. The resistors are 430 ohms, but something in the range of 400 to 750 ohms should be fine. And a 28 pin or even 40 pin ZIF socket. And that's all you're going to need to make this. Now let's take a look at the construction. For so many pins and sockets, it comes apart quite easily. I was surprised that it was not permanently locked together with that many pins. Okay, no mods required to the Arduino board. Okay, there's a good bit of wiring that you'll need to do. Here's all the connections. So I have the PLA pin numbers 1 through 28 going down the left, and these are the Arduino board connections. Most of these are the digital input-output pins, and there's ground and positive 5 volts. So pins to note are pin 1 is a no connect. 14 is the ground and 28 is the plus 5 volt connection, and there's one more input pin, 19, that also needs to be grounded. And other than that, we're just going to make 24 wired connections from PLA to Arduino. 16 of them are going to be inputs to the PLA, and 8 of them are going to be the outputs from the PLA. Okay, so all the digital IOs of the Arduino are over here on this pin header, and these map directly over to the pins here. So I made my connections there. Going down the pins of, now we're looking at the back side of the PLA, so pin 1 is here and it's not connected. So we go 2, 3, 4 and so on down to 14, which is ground. And I used a heavy piece of wire. This is actually solder wick, but you can use a heavy piece of wire for your ground. I just wanted a good connection so there's not a lot of chance of ground bounce. So this is the ground side of a local capacitor for power supply decoupling. This is, I think, a 0.1, yes, this is a 0.1 microfarad, which I forgot to mention earlier. That's the only other capacitor in the design other than the bulk 10 microfarads. And its other end is connected to plus 5 volts, which is over on pin 28 of the PLA. These are the resistors that connect the LEDs. So the plus 5 volts is brought to each resistor. Then the resistor wires through an LED, and an LED wire, and the LED connects to each of the output pins of the PLA. So we were at pin 14, hopping across. There's pin 15. 16, 17, 18, so on. Here's 19, which is grounded, and all the way up to 23, and then 24 is plus 5 volts. So I built this in stages. I didn't apply this epoxy at the very beginning. I made all my wired connections, and I used tape just to hold them in place so they didn't get pinned between headers as I sandwiched the boards together. And I did some testing of the board to make sure everything was working. And then later I came back and added the LEDs, later I came back and added the LEDs and resistors and epoxied the wiring in place. The capacitor is just hot glued down to the board so that it doesn't move and get its leads broken. The LEDs are scattered around here. I've numbered them, and they got really out of order because originally I had them in order from top down to bottom. It was 8, 7, I'm sorry, 7, 6, 5, 4, 3, 2, 1, 0. But I found I had some interference right up here, because when you connect the boards together, this connector actually touches the very back of the board right about here. I had to clear that area out of any of the LEDs and resistors that were on the back. So LEDs got out of order, and it ended up with 7 and 6 down here, and 0, and then 5, 4, 3, 2, 1. Okay, and about the LED and resistor wiring, the reason that they're even there is not just to have LEDs that look pretty. That's nice, but I wanted to have some load on the PLA output pins so that they have to do some work to prove that they're working. So the LEDs are set for about 3 to 4 milliamps of current, and that's a decent sized load to make sure those pins can really pull fully low. So those outputs, the 8 of them, are pins 10 through 13 and 15 through 18. So what you want to do for the wiring is, of the LEDs to these output pins is, let's say this is your 5 volt bus wire, and you're going to bring the 8 resistors off of there to the anode of an LED, and then to an output pin, either 10 or 11 or so on up to 18. These are the 430 ohm resistors, and these are your green LEDs. And with most LEDs, the long leg is the positive. And also, it's not very obvious on this one, but on some of them there's a more obvious flat side, and that's usually your negative. So you can look for the long lead positive, and for the flat on the plastic part as the negative. And it's like that. So anode, cathode, this is the long lead here. Now we'll reassemble this and we'll go start doing the testing. And it does go together very easily, and this is why I epoxied all the wires in place, so that I wouldn't very easily crush one of them or get it jammed there. Right, it doesn't take too much force after the first time or two that you've put this together. And I picked up 5 volts and ground from these 2 pins on this header. Actually, I picked them up right down here on the back side of the connector that's on the other side of the board here. So it says reset, 3 volts, 5 volts, ground, ground. So I just used one of those grounds and the 5 volts. And one thing that I'll point out that I made the mistake of, I initially had one of my LEDs here, and I didn't realize that these pins were, just like these pins are connected to this connector. Well, this array of pins is connected to the pins on the sockets on this socket row here. So this was a ground, and my LED was being grounded, and it was forcing one of my outputs low. So that took a minute to figure out what was going on there. Otherwise, these other pins, although they are routed to the Arduino, they're not being used by the Arduino, so they're floating pins, and they don't interfere with the outputs and LEDs. And up in this area, I don't think there were any dedicated connections already made by the board in this little pin array here. And that's it for the board assembly. Very simple. Mainly, it just takes a little while to make all those wired connections. The wire that I used was something that I found on eBay. It's wire wrap wire, and I'm thinking this was the 30 gauge, but I'll put a link to the actual exact part that I purchased down below in the description. But it's 8 colors, and it really helps you keep things straight if you just follow, sort of like the resistor code. If you just sort of follow the black, brown, Roy G. Biv, then you can order it on the pins, and everything it follows that pattern. It's easier to keep the wire straight. Now let's take a look at a little bit of background so we can see how the software is going to work. So this is the schematic symbol of the PLA chip. And I mentioned in an earlier video a little bit of the background, a little bit of the theory of how this chip works. Not too deep, but just a little bit of it. I'll link that video up above. And basically what's going on here is there are 16 inputs shown on the left. This is the I0 through the I15 input. And then there are 8 outputs shown on the right, F0 through F7. And the software is going to drive the Arduino's digital output pins, and those are wired over to these inputs. And then when a value is driven to these pins, a few hundred nanoseconds later, the outputs will settle to stable values, and then the Arduino will read the 8 output signals into some other digital I/O pins on the Arduino. In the software, I used a couple of variables. One was named input vec and one is named output vec, and they are unsigned integers. 16 bits and 8 bits respectively. And the bit ordering in those variables are from top to bottom, so from CAS down to VIC address 12, that's bit 15 down to 0. And then on the outputs, it's ordered bit 7 down to 0. Now that looks like, and it is opposite, it's the reverse bit order from the numbering shown on the schematic, but you'll see later this just makes it easier to keep track of the signals when we're looking at the logic tables for the PLA. So this is just the lookup table, so you can see which bits in the variable names or in the variable data correspond to which of the signal names. Okay, this table is taken from an old article from the Transactor. Let's go take a look at that newsletter right now. So this is so cool. Back in the March 1986 issue, look right here, revealing the Programmable Logic Array. Somebody figured out how the part works all the way back in 1986, just a few years after the Commodore was released. Let's take a quick look at the article. So, Commodore 64 memory configurations, William Levak from Ann Arbor, Michigan. The major obstacle to understanding the Commodore 64's memory is this 82S100 Programmable Logic Array. And if you have early versions of the Commodore, you can find that the chip was actually originally labeled 82S100 on the old boards. Boards from 1982 and in that era probably have the original 82S100 before it was later re-identified as a MOS chip. And he goes on to say, what we really need is the truth table. And he says, Commodore has not published the truth table. I have therefore read out the chip and obtained the truth table, which is shown in the first table. And so there's about a page here of explanation of some of what the PLA is doing. And then he's referring to this table. And I've copied this table into the presentation. So this one picture completely describes everything that the PLA is doing. Here are the 16 inputs, and here are the 8 outputs, and a way for you to interpret for a given set of inputs what should be happening on the outputs. We'll come back to that, but I want to show you this other interpretation first. This is in a document called PLA Dissected by Thomas Giesel, and he refers back to that document from the Transactor newsletter, and he says that everything in that logic table was correct. He said there were some errors in some following tables that described the various memory modes of the C64, and he's corrected them in this document. But anyway, this is just another look at that same logic. He's just formatted it a slightly different way here. But back to the original Transactor version of the logic table, let's take a look at function output 7 down there at the bottom, this ROM high. So the way that you read this is, since the ROM high has this little bar over the top of it, it's an active low signal. So here are the 3 different ways that ROM high can become active low. Okay, so each of these 3 columns of inputs will fire the output, so to speak. It will activate the output, active low. And if you look at each of the different outputs, you can pick one of the columns to find, one way that you can activate that output. So if you had a program, which we're going to look at in just a minute, that could drive the inputs to a set value, then you could use this value up at the top to tell you, what type of number to plug in to get a specific output to be activated. So you could choose these sets of inputs, drive them in a specific way, and you could individually activate these outputs. And just as a reminder, the variable name input_vec has a bit ordering like this, and output_vec is like this. So let's take these examples. If we wanted to activate the ROM high output, active low, then we would want to, one value that we could put in the inputs field would be FFFB. Now, for those of you who already know binary and hexadecimal and the conversion back and forth, this is probably obvious, but just real briefly, in case someone is not familiar with it, an F in hexadecimal is a 1111 in binary, so that would be a 1 here, 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 and here. Then the next F would be 4 more binary ones, and they would correspond to VA14, A15, A14, A13, and then the third F would correspond to these 4, and the B would correspond to these 4. So the X means it doesn't matter what value is there, 1 or 0 works. So I just arbitrarily chose F. So let's put an F here, let's put an F here, then this must be a 1, so I chose to put another F here, and then 1011 is a B in hexadecimal. So F, 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 B. And it just works the same for each of these select values. So what I'm doing here is I'm just finding a way to activate each of my outputs. So to activate the ROM low output, active low again, I would enter an FCDB, and that sets these specific bits to zeros. And you can just look at each of these columns, and these are the values that would work to drive certain outputs low. Okay, let's take what we just learned and go look at the hardware and see if we can drive these inputs in and receive these as outputs. Okay, so I have the PLA chip installed. This is the Plankton chip, or PLA replacement chip. So I always put the chip in with power off, and when the chip is in, then I connect the USB power, and the USB 5-volt connection is all we're going to need to power the whole thing. Okay, so we have power indicated by that LED, and just as a quick review, I've marked the LEDs by bit number in my output vector variable. So they're out of order, but this is bit 0, 6, 7, 1, 2, 3, 4, 5. So in the example, we're going to try to light the LSB first, bit 0. So we're going to be expecting that LED to turn on. So let me go show you a little bit about the software, and then we'll come to these values. Okay, during the course of bringing up the hardware, I ended up writing about 4 programs, and they varied from, in the beginning, almost completely manual until by the end it was completely automated. So let's open up the first one. This is an INO sketch file, and I have the Arduino IDE installed. I think it's version 1.8.13 or whatever is the latest right now. But anyway, you can double click on the INO file and it'll bring up the software. And this is the file. So all the code is in this one file, and again I'll provide these sketches. So here's the output vector that we talked about being an 8-bit integer, and here's the input vector. and there are two functions in this program. There's the setup, and then there's the loop. Okay, so without getting into too much detail of this program, we can look at this later, or you can see it on your own later. Let's just run the sketch. Let's go check the tools menu. Make sure that you have the correct board selected. Every now and then I come in and it's defaulted back to the Uno board, and I have to occasionally set it back to the Mega 2560, and just make sure it's detecting your COM port. Sometimes this will be grayed out, and you may need to close the software or reconnect the USB cable perhaps, and then reconnect the cable and then start the software, the IDE back up. Anyway, if we look all good here. So I can upload this program, so it'll go ahead and compile it. It will upload it into the Arduino, and then it'll launch it. Okay, so it's there, and now I can click on the serial monitor, and it prompts me for input. It says you can enter your commands either as a 16-bit binary number or as a 4-digit hexadecimal number. Okay, so let's go take a look. What was that command that we wanted? So we wanted to see if FFFB creates an active low ROM high output, or ROM H active low. So if we input FFFB, we would hope to get out an FE, and we'd want to see the LED 0 go low. So let's go try FFFB. So I'll enter X for hexadecimal, FFFB, and enter that. And okay, good. The LED did turn on, so that output is now active low. So the LED, remember, it was wired so that the high side came from the 5 volts. So the PLA output has to go low to make current flow through the LED. So that's why the signal going logic low actually activates the LED. Okay, so that's good. And it says, hey, you wanted to drive the inputs with, here's the binary version of FFFB, and then here's the hexadecimal version, and it says, here are the outputs. So there are the code, so the program measured the 8 digital inputs and found them to be FE, and that is 7 ones and a 0, and so everything's making sense. Okay, let's go look at the next code. It's FCDB, and we want to see an FD. Okay, that is bit 1 LED right there, and sure enough, FD. So let me move this over here so we can see all of them, and we can just type them in real quickly and confirm that they're all working as expected. So the next one is FECF. Do we get an FB? Yes, FB, we got an FB. Okay, how about FFFB? FFFB. Oh, I must have a typo because that's the same as that one. So, oh, clearly, yes, that should have been a 7. My mistake. Wonder if the rest of these values were correct. No, that's not. So 7 E C F. Seven ECF. Okay, let's see. We got an F3. 2 bits went low, and they were corresponding to 3 and 2. And you may say something's wrong, but actually, in fact, this is what would be expected, because not all of the inputs drive only one output. Some of the inputs can drive 2 outputs, and this must be one of those input combinations. So let's see, what are bits 3 and 2? They are, let's see, 0, 1, 2, 3. So they're the read, write, low, and the I/O. I/O and read, write, low. So it looks like this is an I/O access and it's a write operation rather than a read. So it's plausible that that could be the case. Now let's see if, does it make sense that a 7ECF would activate this signal and this signal? We can check that real quick. So if we plugged a 7ECF into this field, now, and there are 6 different ways we can get the I/O activated. These 6 columns. So if any of them would correspond to a 7ECF, then we've explained it. So let's just quickly see if any of these look like a 7. That's not. That would be definitely not a 7. That would be more like a 5. So it's not that one, and it's not that one. Okay, so we need a 0 in this position for the E. So we would need a 0 here, and all 6 of these fit the bill. And they would need 2 zeros here to get a C. So it looks like any one of these 3 would work, except that one, the third one was out because of this 0. So okay, maybe these 2 columns are still in the running. And then finally an F. Okay, so this one's out. So it looks to me like this column right here would light up if we applied a 7ECF. Let's check that. So a 7 would be 0, 1, 1, 1, check. And then an E would be 1, 1, 1, 0, check. And then a C would be 1, 1, 0, 0, check. And then a 1, 1, 1, 1. Okay, so it makes sense that both bit number 2 and bit number 3 lit up on this input vector. Okay, moving on to the FFFD. Okay, now we got LED number 4 or bit number 4. That's correct. And it's an EF. That's correct. Okay, then there are 2 more to check. And that would be FDDF. Okay. Looks like I skipped over, did I skip bit 5? This went to bit 6. Let me go back and touch on bit 5 just to make sure. That was FFFD. Okay, 7ECF. F3, that was bits 2 and 3. And then FFFD. We were expecting a EF. Okay, there it is. Okay, bit 4 is an EF. Okay, now let's go on to FFDF. That's good. That's bit 5, and we got a DF, and DF is what we expected. Now let's move on to the FDDF. Yeah, looks like I had jumped ahead earlier over a couple columns. Correct. That moved on to bit 6, and we got a BF, and BF is what we expected. And finally, oh, this one's a little tricky. This one is, let's take a look at this really quickly. So if you look at the CAS/RAM output, the 1s are all the ways that it can be deactivated. So this table has one little shortcoming, and that is that it's not really clear about exactly how you make the CASRAM signal go low. So it just says that for it to go low, this is in bold because these are the default values. So anyway, it's saying for the default input, we should get the default output of 0, but it doesn't tell us what the default input is for CASRAM low. Well, it turns out one way of getting it is 7FFF. In fact, there are a lot of ways that CASRAM can go low, and I'll show you more on that later, but it is the most commonly low signal of all these. But anyway, let's try the 7FFF and make sure that we get this 7F output. Sure enough, we see LED bit number 7, and we get the 7F. Okay, so that was the first program. That was the way that I determined whether the wiring was good. Also, let me mention, you want to do a full ohmmeter check before you apply power, and I did a full check. I checked for 5 volts, and I checked pin to pin for any shorts, and there were no shorts. I checked all the wiring with a multimeter, my DMM, before I even applied power. And then this first program was just a good double check to make sure that everything was working at least close to intention. The next program is one that will allow you to do a search for all of the input combinations that will trigger a specific output bit. So I'm going to compile that, upload that, and then we'll run this program. Okay, this says the program searches for all the input combinations that activate a certain output bit. Choose an output bit to activate, 7 down to 0. Okay, let's say we wanted to activate the basic output, that's bit number 6. And then it says, which level do you want to match? And I'm going to choose the level 0 because that's an active low output. And all these signals are active low outputs, other than the read-write, which is read high or write when low. And then there's a lot of flashing going on. What it's doing now, it's going through all 2 to the 16th power, all 2 to the 16 possible input combinations. So there are 65,536 possible inputs. It just went through all of those, and it looked for any outcome where bit number 6 was low. So let's see, does that make sense? Okay, so it started with the all zeros input and worked its way up toward FFFF, and anytime bit 6 was low, it printed the results. So you can tell a couple of things by looking at this result. I went ahead and I pulled this into a spreadsheet, and I found out that there were 256 different ways that we can get the output of bit 6 being low. The other thing I noticed was that it's always BF, so whenever bit 6 goes low, only bit 6 is low. So it's one of the mutually exclusive outputs. So for whatever reason, when the basic output signal is active, no other outputs happen to be active. So that's just the way it works. So there were 256 ways that the bit 6 could be activated. And you can run this program again and try it for any of the outputs. Oh, and I mentioned before, bit 7, the CASRAM, is the most commonly active output signal. Let's just try it. So I'm going to press the reset button. Actually, I'm going to clear the output in the terminal, then I'm going to press reset. Now we're going to choose bit 7. Again, active low, 0. And it looks like almost every input code, input variation is lighting up that bit. And that is the case. Almost half of the, or probably about 3/8 of the 65,000 and some input combinations will activate bit 7. So it takes quite a while for it to go through all of these combinations. And what's actually taking most of the time is not the changing the inputs and measuring the outputs. It's the printf statements that's printing to the screen. The serial port carries these print statements, and it's only running at 115 kilobits. Okay, it turns out that once we get to 8,000 hex, no more of those input combinations from there up will activate bit 7. So the search was over by 7 FFF. It went all the way up just to check. Nothing above 8,000 fired that output. And again, I took and exported all of these codes into a spreadsheet and did some analysis of them offline just to see if I could figure out how this thing worked. So it turns out you can decode the inputs that the program discovers, and you can actually reverse engineer the logic equation that exists for each of the output, and you can come up and derive the logic table on your own if you'd like to. It's quite a it's quite a time-consuming process, but I actually went through it and verified it, and it can be done. So you could create this logic table by running that program for each of the 8 outputs and then analyzing the values to get the truth table. Okay, so this sketch is actually the one that I use finally to just go and test the PLA. I would set the verbose flag to false, and that way it doesn't print out too much information and slow the program down. So let's upload this one. And it's starting to run immediately. So it's going through all 65,000 and some possible inputs and checking for the expected outputs, and it's finished. Okay, when I opened the monitor just now, it restarted the program and it's running again. So it just says starting test. This can take up to 1 minute. Well, it's not going to take anywhere near 1 minute. Okay, so it says all the vectors passed out of all possible vectors. So this is the test that I would run when I'm just testing a PLA chip. And if you want to see a little bit more information about what's going on, you can turn this to true, re-upload. And then it turns it into one of my earlier programs that I wrote that just shows, going through in brute force, it displays every input combination and the resulting output. It calculates the expected value, and so it's printing the outputs that it measured versus what it expected for every case of the inputs. And it takes a lot longer, like we were saying before, just because it's trying to printf all of this text to the display. I'll go ahead and skip to the end. Okay, it's finally complete. That took, I think, about 5 minutes. It seemed like a long time to print all those statements. Okay, so let's go back to false. Upload that. So I just wanted to look again at how much quicker it is when we don't printf all of that information. Let's run this program. Right, I think this is going to blink about 16 times, and that's how I can tell when it's just about to finish. Okay, we're there. Okay, that was a lot quicker. One thing I wanted to say is there's probably a 4th or 5th program that could be written, which is a simplified or a short version of this complete one. So the complete one is called Tester Complete Equation, And again, it's doing a full check of every possible input combination. But a much quicker test, if you're mainly concerned about test time, and maybe you're testing a lot of PLAs and you just want a quick result for each of them, what you could do is you could just test each pin, each output pin can go high and low. So basically just do a stuck at test for each of the outputs. Make sure that some input combination can make each one of them go high and low. So for example, if you started off with the all ones input, then you should get an all ones output. In fact, we can try that real quick. PLA Tester. The original one. The one that I used for hardware bring up. Let's compile that and upload that sketch. Okay, so if you enter the command inputs all ones, then you get an output of all ones. So at this point you already know that at least all the pins are high, as they should be. And then you can just do what we did earlier and make each of the 8 outputs go low. And it turned out there were 7 input values that turned on either 1 LED or 2 LEDs. So I'll probably go ahead and do this, or you could even do it yourself. You could take either one of these programs. You could either take the PLA Tester and take out the user input portion of it and just make it go through, what would it be, 8? You'd probably want to go through maybe 16 different inputs. You'd start with the all Fs, and then you would go to the bit 0 output, make sure it can go low, and then you'd come back to the all Fs to make sure everything returned high again, and then you just walk through each of the outputs. So with about 14, 15 different checks, you could say with pretty good confidence that this is a good PLA. I just hadn't taken the time to create that one yet, but it makes sense that you'd want maybe a thorough test and then maybe a quick test. Then you, depending on your preference, you may prefer one or the other. Personally, I don't mind doing the thorough test if it only takes about 10 or 15 seconds. So I would probably run the complete test every time. And I think that's all I need to go over on the software. Perhaps we could do a walkthrough of the C code. Yeah, why don't we walk through the C code just to get an overview of how the source code is set up. Okay, so this is the tester complete equation. This checks all 2 to the 16 input combinations and compares the output that was measured to the expected output results. It's a short program, so let's just go through the basic sections of it. So I have some global variables at the beginning, and then I have mask values, or mask constants, and comparator constants. So these were derived straight from the logic table. So each one of these corresponds to a column of the data in the PLA Dissected document. Okay, let's just take a look at this table for a second. So there are 32 columns, and they're numbered from 0 to 31. So that's why I have 32 different masks, or 32 different comparator constants. So for the mask, what you would do is you would just read down the column, and if a bit is used, then it's either going to have the asterisk or the slash. So the mask corresponds to which bits are being used in this column. So here, this bit and this bit are used, these 3 bits are used, these 2 and that one, and so on. So the mask would be 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 0. So in hexadecimal, that mask value would be what? 6, 7, 3, 4. Let's go back over to the code. 6, 7, 3, 4. Okay, let's look at one more example. Let's look at the last column. Okay, this column would be, again, it's the bits that are being used. So it would be an 8, 7, B, 0. Sure enough, 8, 7, B, 0. Okay, then the comparator constants are similar to that. Okay, but the difference is, okay, now we're ignoring any bit that wasn't used. Now we're just saying, should the bit that's used be high or low? And if you read about this table, the asterisk means this bit needs to be high. The slash means this bit needs to be low. So the comparison value is all the asterisks need to be 1s and all the slashes need to be 0s. So it would be 0, 1, oh yeah, and the unused bits are also 0. So it would be 0, 1, 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0. Okay, so what would this be in hexadecimal? That would be 6, 5, 1, 4. 6, 5, 1, 4. Sure enough, 6, 5, 1, 4. Let's just check the last one. Okay, this is a 0, so these are all 0. Here's a couple of 1s. So that would be a 6, 8, 0. So 0, 6, 8, 0. 0, 6, 8, 0. Sure enough. Okay, so that's how the mask and the comparison values work. And then there's just some setup code. We set up the serial port. We initialize the input vector to all 1s. And then we specify which pins are the output, digital outputs. And we set them to the high state. And then we set which pins are the input pins. Okay, then in the loop, okay, we run from 0 to 65,535, and each loop we increment the input vector. So it starts at all 0s, and then it goes to 1, 2, 3, and so on, all the way up to 65,535. Okay, we take a copy of the input vector because we're going to shift it out into the output pins. So we perform 16 shifts and call the digital write. This sets an Arduino output either high or low. So in this for loop, we drive all 16 of the output pins. And then we calculate the expected output value from the PLA. So we just go through the 32 different mask constants and comparison constants, and we calculate the 32 different P terms. And the P terms are product terms in the logic array, and that's what these 32 columns stood for, the P term 0 through 31. And so it just calculates whether a P term is set. So for example, if the 0 P term is set, then that says that CASRAM is high, and it says that the basic output is low. So the way this row works is, this is saying if there's a plus sign here, it means that the output is the OR of any of the p terms that are set, that are true. So if any one of these that have the plus symbol, if any one of those p terms are true, then CASRAM will be high. And if none of them are true, CASRAM would go low. Let's take the basic output. This is saying it's an active low output, and it's active when p term 0 is true. So p term 0 is the only p term that affects this output. But the kernel output is fired by two different p terms, p term 1 or p term 2. So what the code does, it just goes through each of the, calculates each of the 32 p terms, and then it combines the p terms to determine what the 8 outputs should be equal to. So let's see that quickly. Okay, so at this point we know all 32 p terms, and now we just determine what the expected output vector should be. So this is where we analyze the p terms 0 through 31, and we update the expected vector, and when we come out of this, expected vector should equal the outputs of the PLA. So in this for loop, we read the 8 digital inputs that come from the PLA, and then we make a comparison of that 8-bit output vector from the PLA and compared to the 8-bit expected vector. I don't yet know where I'm going to archive these files so that you can get access to them, but I'll definitely make them available to you, and I'll have some directions in the description below this video. Okay, so we saw the tester work just fine on the Plankton, but what about a real PLA? And by that I mean the original PLA. So let's try one. I actually have here one of the original 82S100 parts before this became a MOS chip. So this is the programmable mask device. You could probably read the design out of this, and it's probably what Mr. Levak did back in 1986. He probably used one of these type of parts. Okay, and let's start up the complete equation test. This is the thorough test that tests all 65,000 combinations. Let's upload it. It's already running. So I can tell already that it's actually passing so far, because if it fails, it stops at the first failing vector that it encounters. So let's bring up the serial monitor. Okay, and the test is started. And one note about this is, as long as the LEDs are flashing, the test is still running and it's not finding errors. If it found a failure, it stops on that error and it displays what actually failed. Let's take a quick look at the code and see what that would look like. Okay, so it would say, hey, for these inputs, these are the outputs that I measured, but I expected this. Okay, so let's, to see that in action, let's change something. Let's change this 27 to, I don't know, a 38. So I'll just keep that there. Change anything. Should make something fail. Upload that. Okay, it's running, it's running. Oh, okay, something must have gone wrong because it's paused. And let's see. Okay, it says error for the input 2710. The output was DF, but it expected a 7F. The test is complete. There were 10,000 passing vectors out of 10,001 total. So the 10,001st vector was bad. At least we can see that it's working, and it tells you what failed if something fails. I guess in another version of the software you could, in another version of the program, you could have the option to continue on and just keep testing and printf anything that fails. Well, in fact, let's go ahead and do that. So let's say if it fails, let's print the error message, but let's don't break out of the outer for loop. Let's just let it run. Okay, compile and upload. Okay, it's off to the races. Let's see what happens. Okay, it's displaying errors. Lots and lots of errors. So I suppose you could look at the bits that seem to be affected to get some idea of what must be wrong with your PLA. So if it expected a 7F and the output was DF, you could conclude that you have two outputs that are wrong, because the D is a 1101, but the 7 is a 0111. So a couple bits went wrong there. Okay, let's make a smaller change. I changed several bits. So let's make a more subtle change. So from a 27 to a 07. So a little bit less of a disturbance in the expected values. Compile and upload that. Okay, it's going. Okay, we're getting several errors again. Okay, so you can see sometimes we expected an FF, but we got a DF. So one output went low when it shouldn't have. DF, FF. Let's see if there are any other. Everything's okay. Here's a. We expected a 7F. We got a DF. That was similar to the before. All right, good. So as you can see, the program will tell you exactly what failed, or at least it'll tell you which bits, and you can determine for yourself which signals those correspond to. But I'm going to return this back to the correct values, and so you can take this break statement in and out to let me say comment this line to continue testing upon failures. To continue testing after failures. All right, that wraps up the PLA tester. I hope this was helpful for at least a couple people out there. So if I make any updates or write a new version of the program, I'll definitely let you know in the description below the video. Definitely want to go through my collection of Commodores now and start culling out those ones with suspect bad PLA chips. So that's it for now, and until next time, see you then.